Welcome to Sunil Maths tutorial. Functional analysis class number 68. In this video, we prove a theorem. Let us see the statement. If capital M and N are closed linear subspaces of a Hilbert space capital H and P, Q are the projections defined on M and N respectively, then M perpendicular to N implies and implied by PQ is equals to 0 implies and implied by QP is equals to 0. Another important theorem for examination. Let us see the proof. Let capital H be a Hilbert space, capital M, N are closed linear subspaces of capital H, capital P, Q are projections, capital P, Q are projections defined on Hilbert space capital H, but particularly on M and N respectively. It means P is a projection defined on M, Q is a projection defined on N. Both P, Q are projections defined on M and N respectively. By the definition of projections, we have P star is equals to P, Q star is also equivalent to Q by the definition of projections. Seriously, first we observe that PQ is equals to 0 implies and implied by PQ whole star is equals to 0 star implies and implied by Q star P star is equals to 0. Q star is nothing but Q, P star is nothing but P is equals to 0. Therefore, PQ is equals to 0 implies and implied by QP is equals to 0. This is a very simple calculation. We have to show that. Our aim is to show that. We have to prove that. M perpendicular to N implies and implied by PQ is equals to 0. Now our aim is to show that M perpendicular to N implies and implied by PQ is equals to 0. Already we show that QP is equals to 0. So the theorem will be completed. Suppose M is perpendicular to N. Our aim is to show that PQ is equals to 0. Let Y be any vector in N. Since M perpendicular to N and Y belongs to N, it means Y is an arbitrary vector in N. It means Y is orthogonal to every vector in capital M. Y is orthogonal to every vector in capital M. If Y is orthogonal to every vector in capital M, then Y belongs to M perpendicular simply. Therefore, you observe that we choose Y belongs to N. We prove that Y belongs to M perpendicular. This condition implies as N is subset to M perpendicular. Right, now, next, let us take Z be any vector, arbitrarily chosen vector in the Hilbert space capital H. Z is any vector in H. Then QZ is in the range of Q because Q is a projection defined on capital N. Therefore, QZ is in the range of capital Q. It means this QZ belongs to capital N. If QZ belongs to capital N, already we show that it is subset to M perpendicular. By observing this, QZ belongs to M perpendicular. If QZ is belongs to M perpendicular, and it is very clear, M perpendicular is null space. M perpendicular is null space of P. Null space of P. If M perpendicular is null space of P and QZ belongs to M perpendicular, implies as PQZ is equals to 0. Actually, you can write like this: P of QZ is equals to 0, which shows us PQZ is equals to 0 for all vectors Z belongs to H. This condition implies as PQ is equals to 0. Here Z is not equals to 0. Here you should take Z not equals to 0 belongs to capital H. So PQ is equals to 0. Therefore, we assume that M perpendicular to N. We prove that PQ is equals to 0. Already we show that QP also equivalent to 0. So right, that's it. Now we go for converse part. Converse. Suppose PQ is equals to 0. We can show that N perpendicular to M. To prove this, let us take two vectors, X belongs to capital M and Y belongs to capital N. Now take two vectors, X belongs to capital M and Y belongs to capital N. Now consider the inner product. Now, okay, before going to define the inner product, now write two more steps. Since capital M is the range of P, which implies Px is equals to X, and capital N is the range of Q. Then Qy is equals to Y. Now we are going to define the inner product. Now inner product of X comma Y is equals to X equal to Px, Y equal to Qy. So already we learned some properties. Inner product of Tx comma Y is equals to inner product of X comma T star Y. So by applying that property here, it can be written as inner product of X comma P star Q into Y. In the introduction part, we said that P is a projection, so P star is equals to P. If P star is equals to P, then obviously X comma PQY. Here in the converse part, we assume that PQ is equals to 0. So you can write this step as inner product of X comma 0 Y. This is nothing but inner product of X comma 0. Inner product of X comma 0 is nothing but 0. Therefore, we show that inner product of X comma Y is equals to 0. What it means? X is perpendicular to Y. Therefore, we show that X belongs to capital M, Y belongs to capital N, implies as X perpendicular to Y. This is true for all X belongs to M and Y belongs to N. Therefore, M is perpendicular to N, or M is orthogonal to N. Hence we conclude that M is orthogonal to N, implies and implied by PQ is equals to 0, where P is a projection defined on M and Q is a projection defined on N, and both M and N are closed linear subspaces of the Hilbert space capital H. That's it. This completes the proof of our theorem, hence proved. In the next video, we'll learn orthogonal projections and definition of orthogonal projection, and a theorem depends upon the orthogonal projection. Keep learning.